telescope. The question that I got, if you didn't see it on Canvas, was to go back over radioactive half-life and half-value factor. So that's what we're going to start with, and then I'll shut up and give you all a few minutes to look over your notes and see if there's anything else you want to talk about, clarify, and then we'll call it a day after that. So radioactive half-life, we'll start there. Radioactive half-life is the length of time that it takes for any kind of radioactivity to disintegrate or decay to half of its original intensity. So I'm going to use some numbers, but the numbers don't really mean anything. I'm just using the numbers because it'll be easy to calculate, and I'll show you how to calculate it. And my recommendation for calculating it is to do it as simply as possible. Use a scratch piece of paper and completely draw it out. Otherwise, you're going to have a tendency to kind of trip over, and instead of taking it step by step, you're just going to have a tendency to make a division problem out of it, and in most cases you're going to get it wrong. Okay? So, radioactivity or radioactive substances all have specific half-lives. So carbon-14 is different from potassium, whatever, and they go from, carbon-14 is, as far as natural radioactivity, has an extremely short half-life, but it's still over 5,000 years, as opposed to some of your potassium-based radiation is hundreds of thousands of years. Okay, so if we were to take carbon-14 and we just rounded it down to 5,000 years for the half-life, it's not completely accurate, but it's an easy number to keep up with. And we have a quantity, so I'd recommend on the test you just draw a big circle. If you have a quantity of carbon-14 or any kind of radioactivity, and let's say the half-life is 5,000 years, what that means is that for the quantity that you have, and again, the unit that we use doesn't really matter. Let's just say we have 100 somethings of carbon-14 or whatever this radioactivity is, okay? Don't get tied up in the curies versus the rad versus the rem versus any of that, okay? It doesn't really matter what unit we're measuring in. We've just got something that it takes 5,000 years to cut it into half of that. Okay, so we've got 100 units of this stuff, and it takes 5,000 years for it to cut it in half. What that means is that in 5,000 years, as half-life number one, is 5,000 years, how much we're going to have? We started with 100.
50.
Yeah, so we got 50, right? So that's one half-life. So one half-life later, it's 5,000 years, we've got 50, whatever we started with. So we have half of what we originally started with, okay? So in another 5,000 years, that disintegrates in half again. So in our second half-life, if we started out with 50, so the clock starts all over again after 5,000 years. So in 10,000 years, 10,000 years, that is the second half-life, so that's 5,000 plus 5,000. That's not 10,000 years after this, but 5,000 years after that one. Then what we're going to have is half of that, so we're going to have 25. All right? So two half-lives at 10,000 years. It's two half-lives. What will be half-life? Second half-life at 10,000 years, we got 25. So a third half-life is at 15,000 years, and again, make sure that you don't confuse that, that's not 15,000 years after this one, that's cumulative 15,000 years, so that's third half-life. How much we're going to have? 12.5. 12.5, right. So again, it divides what we've got left, the clock restarted, and what we've got left is 12.5. Okay? So at the fourth half-life, we do it all over again. Fourth half-life, we're now sitting on 20,000 years. So that's half-life number 4 at 20,000 years. How much will we have?
6.25.
6.25, so we cut that directly in half again. And what we have left is 6.25. And then we could do it again, and we'd have 3.125, and then we'd have 1.6725, something like that. So each half-life represents that 5,000 years. So, your question may say, you start off with 100 curies of some radioactivity, and half-life is 5,000 years. How much are you going to have in 3 half-lives? Well, 3 half-lives, you would have half of what you have in 2 half-lives, which is half of what you have in 1 half-life, which is half of your original. So you just divide each subsequent half-life by 2, so you have 12.5. It's 1 dot.
You said don't worry about the units?
Don't worry about the units,
Okay.
I'm gonna give you the unit, and, so you just have to match it up, if I asked you specifically about curie and you gave me pounds, I don't think it's that specific on the test, but, don't worry, don't get stuck in the minutia. What we're looking at is primarily the division and taking it one at a time.
So meaning like we don't have to worry about like converting units?
Convert it from rad to rem to curie and all that?
Yeah.
No. Trina will get into that next semester. The reason that I brought that up was just, the quality of radiation, the difference between curie and all, and the rads in the rem, is primarily just to show the relative danger of the different types of radiation. Alpha particles are extremely dangerous and give a tremendous dose compared to X-rays. X-rays, the quality of the X-ray, and it's not the quality of the X-ray in that, the quality of our ability to make an image as much as it is the relative damage that you can do with each one. The quality of the alpha particles 20 times what it is X-ray. Does that kind of make sense?
Yes.
So there's never a 0% radioactivity? There's no.
Well, that's a good question. Theoretically, yes, but no at the same time. It can get so low that you can't detect it, but theoretically it's still there. And it's kind of like sound, Theoretically, sound never goes away. That if you could measure sound and filter out all the new sounds, you could theoretically pick up a dinosaur's roar, theoretically, because it just keeps getting smaller and smaller and smaller. Kind of the same principle. You can't detect it. You're never going to hear a dinosaur roar unless you watch a movie, but kind of the same principle. It just never completely goes away, but it may become undetectable. So like carbon-14, I kind of touched on this, I think on Friday. Carbon-14 is what we use to radiometric date, right? But we can't radiometric date fossils for a couple of different reasons. One is carbon-14 is reduced to such a small amount by the time something is fossilized that we can't detect it. Last I actually researched carbon-14, it goes out to about 60, 70,000 years before it gets so low that we can't really measure it anymore. But it's still there, we just can't, we don't have the instrumentation developed that it can measure that low a rate of carbon-14. Okay. Plus, in fossils, a lot of the mineralization's been replaced with mud and dirt and whatnot, so there's not really bone anymore. We call it a dinosaur bone, it's not really bone anymore. Okay, so y'all good with that? Okay, so in X-ray, we don't, we're not dealing with radioactivity. What we're dealing with is just electromagnetic energy. And in X-ray, we measure the quality of the X-ray beam in half-value layer. So half-life is radioactivity. The equivalent X-ray is half-value layer. The half-value layer is where we use some sort of absorber, and the most common is aluminum because it's readily available. and it's what we use for filtration anyway. And it's any sort of a predictably thick absorber that would reduce the intensity, which is relative mass. As we go through imaging, you'll learn that mass equals intensity, just numbers. So it's the amount of an absorber that reduces the intensity of the exposure by 1/2, okay? So if you made an exposure with 70 kVp at 50 mass, let's do something easier, because 50 mass, let's say 10 mass. At 70 kVp, for every mass that you create, and this is way advanced, it's not on the test, but for every mass that you create, there's about a 5 MR exposure, okay? So at 50 mass, you're gonna be or 10 mass, you're gonna be creating roughly 50 MR. That's the unit that the physicist is gonna use to measure how much output you've got from your tube. He's not really gonna measure in mass, because to him, mass doesn't matter. It's what's actually coming out of the X-ray tube. This is tube current, really. And that's what we use, just as a mental and visual representation of what our technique is. But to a physicist, it doesn't matter. He wants to know exactly how much that tube is putting out. And what he should see is for every mass that you send, across the tube for that quantity of electrons, you should have that number of exposure, okay? So we've got X-ray tube, we have collimator housing, and we energize X-ray tube. And if we set that technique, that's how much exposure we should have. MR being milliroentgens, being exposure in there. It's not hitting anything. This is the exposure just below the X-ray tube, right? So that's the amount of radiation coming out of the X-ray tube. So if you were to take an absorber, say this is 1 millimeter of aluminum, and with that 1 millimeter of aluminum, what our exposure below that is, so he measured it up here, and then he measures it below the aluminum, and if it comes out to 50 MR, then that X-ray tube's half value layer is 1 millimeter of aluminum. It took 1 millimeter of aluminum to take this exposure and make that exposure out of it. Okay? So that's half value layer. And half value layer is a measure of X-ray beam quality. Okay? So we're going to get a little bit deeper here. This is really what you need to know about half value layer right now. If it took 2 millimeters of aluminum to cut it down to 25, then your half value layer would be 2 millimeters of aluminum. That's basically what you need to know. So if you had a question that said, how many half value layers does it take to get this exposure down to 6.25 or whatever? So 1 millimeter of aluminum, cut it to 25. A second millimeter of aluminum, that's 1 half value layer. 2 half value layers would take it to 12.5. 3 half value layers would take it to 6.25. So basically the same thing, okay? Now how this is a measure of quality, beam quality, and again, this is getting deeper into the semester, is that what we use to affect a change in beam quality is kVp, okay? If you want a better quality X-ray beam, what you do is you crank up your kVp. And logically, you can kind of work through this. If you shoot a KUB on a patient, what kind of technique do you use? What kind of KVP have you paid attention to KUBs? The KVP level that you set?
To 80.
Yeah, it's 80 KVP. So imagine if you were to take an X-ray of a patient's abdomen and you were to use the lowest KVP your machine allows. Well, what do you suppose you would get? If it takes 80 kVp to get a good image, what would 40 do, let's say?
Would it be like really grainy?
It would. That's way deep in this semester, but you would get quantum model probably. It'd be really, really grainy. It might not even make it through the patient. Okay? So what are we trying to do in X-ray? What are we trying to do with our X-ray beam? What does it have to do to give us that shadow image?
Penetrate.
That's penetrate, right? So if it doesn't penetrate, then what quality, what use is it to us?
It's not.
Zero. So quality at that point doesn't exist, right? So KVP is what we use to affect the change in beam quality. Beam quality is penetration. Penetration is KVP, okay? Now, the reason that I say that half value layer is a measure of quality, is actually a better measure of quality than KVP. And again, this is getting deeper into the semester, and this is not, not a testable question at this point. But what happens over the length of time that you use a light bulb?
The light bulb gets
It starts to burn out.
It gets burnt out, and you unscrew the light bulb, and what do you see? What does the bulb itself look like?
It's got black, usually on black.
It's got that black goo on it, right? So what you've got there is actually the filament inside of your light bulbs, unless you're using fluorescent bulbs or LED bulbs. But if you're using an actual filament and incandescent light bulb, that black stuff is actually that filament that vaporized and it's on the inside of the glass. That filament is made of tungsten, just like in your X-ray tube. The filament's made of tungsten, the anode's made of tungsten, and we'll talk about why we use those later in the semester. But if that's going to happen in a light bulb, does it not make sense that it would happen in an X-ray tube too? Okay, so you got a brand new X-ray tube, and remember that everything is radiolucent. We don't have anything that's radioapparent. X-rays will be absorbed into anything that it passes through. Okay, no such thing as radioapparent. It's radiolucent, meaning that some absorption is going to take place there. So we make an X-ray, and some of the X-rays are going to be absorbed in the glass. It may be so little absorption that you might not be able to detect much of it. As a matter of fact, whenever you're working on a trauma case, sometimes if the glass broke in the window next to the patient, sometimes you'll see glass on the image, sometimes you won't. And sometimes you will. The glass will absorb some X-rays, you'll see that artifact. Okay, so glass will absorb X-rays. But if the patient's wearing a buckle, what are you always going to see?
The buckle.
The buckle, right. So metal is going to absorb more X-rays than glass. So now apply that thin coating of tungsten to what you just learned. What's the tungsten going to do?
Absorb.
Absorb, right. So now apply that to William Rollins. What were William Rollins' 2 contributions to radiation safety?
Collimation and filtration.
Collimation and filtration, right. What did filtration do?
Filtered the low energy.
Eliminated low energy X-ray photons, right? So it gets rid of low energy X-ray photons that would just absorb inside of the patient. So when we're looking at the difference between glass and a thin coating of tungsten on the glass, which one of those two is going to absorb more X-rays?
Tungsten.
The tungsten on the glass, right? So every year your physicist has to come in and he has to do quality control. And he might do it twice a year. And one of the things he's going to do is what we call, this is actually second year stuff, so please don't, harp on this just right now. This is just to kind of explain this, fully explain this. One thing that he's going to do is an MR to MAS output, all right? The purpose for this particular test is to make sure that for that 10 mass, he gets 50 MR, relatively speaking, right? But over the course of the year, that filament is going to coat the inside of that X-ray tube, and it's going to absorb more and more of those X-rays, so that at the end of the year, that might not be 50 MR, it may be 45 MR. But he needs it to be 50, because that's what it should output at 70 kVp at 10 mass. It should give him 50 MR. So he's going to have to get into the machine, he's going to have to tweak it a little bit, and he's going to have to bring that 45 back up to 50, okay? So, did he get inside and scrape the tungsten off the inside of the tube?
No, it's vacuum sealed.
It's a vacuum tube, exactly. He can't get inside of it. So, when he lost those 5 MR, What photons do you think you lost? High energy or low energy?
High.
The high kV, the ones approaching 70 kVp, or the ones at the low end? Low end, right. It acted as filtration. You got two different types of filtration. One is filtration that's built into the system, and you can't really change it. Another is added filtration. As the tube ages, what you get is increased filtration that you can't remove from the system. So it's what we call inherent filtration. So as tube ages, we get increased inherent filtration. What's the purpose for inherent filtration? Or for filtration?
Catch more of these photons.
Remove low energy photons, make it safer for the patient, right? So, as the tube ages, the output decreases, the physicist has to get in there and tweak the machine to bring it back up to this output. So what's left? The high energy photons or the low energy photons? The high energy photons. You got rid of low energy photons. So now, enter the next x-ray room over. This was a brand new x-ray tube. So it took 1 millimeter of aluminum to get to a half value. This crusty old thing's been around for a while. You make exactly the same exposure. So you got 70 kVp, 10 mass, that gave you 50 MR of exposure, but this thing's been hanging around for about 3 years. In that 3 years, we've got to build up a tungsten on the inside of the x-ray tube, so the filtration over here is more, right? So since the filtration is more, we've got removal of low energy photons, but to reintroduce the quantity, the number, to bring it back up to 50, 3 years in a row, the physicist had to tweak the machine to get it to that point. So you make the same exposure, and what it might take is 2 millimeters of aluminum to cut this from 50 to 25. It only took 1 over here because a lot of low energy photons. It took a lot of filtration or a lot of aluminum to cut this one in half. It didn't take so much on this one, right? So what do we use to control beam quality? kVp, right. So what does this number represent? I ain't got there yet. It's the highest X-ray photon, the highest energy X-ray photon you're going to create in your beam. So if you set 70 kVp, this is absolutely the highest energy of X-ray photon that you're going to create. Now here's the sneaky little secret. Almost none of them are going to be there. Almost all of them are going to be low energy photons. That 70 represents very, very few. If you were to graph out, again, it's getting way deep into the semester, if you were to graph out the relative incident of different energy level of X-ray photons after they come out through all that filtration, it would look like this. So that the average beam energy would be represented here. This is the highest energy. So if we set 70 kVp, and this area under here represented the numbers at each energy level, what would you say about 70? A lot of them, not many of them. This represents numbers, and this represents energy level, right? So 70 kVp, we don't get a whole lot of them, so that's the peak energy. But if we can take these numbers and reduce the low energy X-ray photons and leave just with the high energy X-ray photons, or more of the high energy X-ray photons, what would you say about the quality of these if kV, not necessarily the peak, but the energy level measured in kV represented the quality of the X-ray beam? Would that be higher, or would this be higher? We got rid of low energy photons here. We had all the low energy photons over here.
Quality, the crusty one.
The crusty one would be better. Yeah, the crusty one would be your better X-ray beam. Okay. Now here's a second sneaky secret: is X-ray beam quality and image quality aren't the same thing. Okay. So in a test, and this gets into imaging for Trina's class, and it gets into imaging next semester. X-ray quality you have to have contrast, and what controls your contrast in the X-ray? What do we use to control contrast? KVP. All right, so the higher the energy of the X-ray beam, the better the beam quality, the worse the image quality. Okay, so as half value layer increases, so it takes more of a absorber to cut the intensity measured in MR in half, we have a higher quality beam, because what we've got is fewer low energy photons and we've got more high energy photons. So our X-ray beam characteristics are more of a bell curve pushing towards a high energy side. Okay, probably got a little deeper than what you necessarily needed to know, but just to kind of wrap it all together and explain why it is, because every year students kind of trip over that. They say, well, I don't understand this old crusty machine shoots better than the brand new machine. Yes, it does. It does, because of it increased inherent filtration, because that filament starts to vaporize and coat the inside of the tube, and it increases the filtration. Purpose for filtration is to remove low energy X-ray photons, give us a better quality X-ray beam. So anything that we do that increases that filtration gives us a better quality X-ray beam. That one. Higher the half value layer, the better the quality. Okay. So does KVP measure quality? Yes. But what's the better measure of quality? Half value layer. Because KVP is identical, right? But there's a better quality X-ray beam over there. Okay? Now I started to lose you there at the end. I can see it in your eyes, but you kind of get it. Half value layer goes up, better quality X-ray. Okay. So I'll give you a few minutes to look that over and see if there's anything else that. Trina said that some of y'all were having a hard time watching the videos.
Yeah.
Yeah? What are you using?
I'm using Chrome, and like,
Chrome.
I've been watching like a couple of them on my phone, but it's really, like, you can't read the board, obviously, because it's too small. So I had to like download something, it didn't work, and then it said to put like in your cookies on your computer like 2 different, I don't know, websites or whatever to put in there, and it still wouldn't work for me. I don't know.
Have you tried Firefox?
Yes, and it
Yeah.
still didn't work. I don't know if it's just my laptop, but I'm gonna go bring it to my mom's house and see if she can fix it. She fixes everything.
Oh, yeah. If she can't, just call the help desk and see if they can kind of
Yeah, I
walk
was
you
thinking
through it.
about even if it doesn't work, just, like, I called them and left them an email and they never messaged me.
Yeah.
So I might just bring it over there and just
Yeah.
tell them, hey,
Yeah.
I need help.
Yeah,
Yeah.
it's not a bad strategy, sometimes getting in somebody's,
Yeah,
not rudely getting in somebody's face, but getting face to face with somebody.
yeah,
Will
they're
make all the
probably
difference in the world.
more willing to help,
Yeah,
yeah.
yeah, it's harder to say no whenever somebody's looking at you. Yeah.
So this test will have math?
It'll have math, and you can use calculator, but it's like that, just divide by 2, divide by 2, divide by 2. The reason I say to break it down like that is because, let's say you start off with 1,000 units of something, and you say, well, I got 3 half-lives, you divide by 3, what do you have? Something like that, right? As opposed to 3 half-lives, if you go 1,000 divided by 2 is 500. And I know I set that up like a multiplication problem, but divided by 2 is 250. Divided by 2 would be 125. That's a big difference, right? So take it incrementally. Don't take a shortcut and say, well, it's 3 half-lives, divide by 3.
Yeah,
You're
so
gonna get
you
it
want
wrong.
us to do the second way, not the first?
Yeah,
Okay.
yeah, take and cut it in half, cut it in half, cut it in half, just draw you a picture,
Okay,
make it a square if, you prefer lines instead of circles.
is it always divided by 2?
Yeah, if it's half-life, it's always gonna be divided by 2, so how many times do you divide it by 2 is the question. So if it's asking for, 3 half-lives, you divide it by 3. or divided by 2 3 times. No, not divided by 3, don't do that. Yeah.
I'm happy you explained this, because I kept watching YouTube videos, and they kept confusing me so badly about how to do this.
Oh, yeah.
And I
They
was
try
just
to
like,
set up a
oh my
formula.
God. Yeah, and I was
Yeah,
like,
just
oh
keep it
my
simple.
God.
Yeah, just keep it simple.
But the test could have the aluminum layers as well.
The aluminum layers is, that refers to half value layer.
Okay.
Yeah. So there are no aluminum with half-life. Half-life is you just set it on a table and let it decay.
Okay.
The aluminum layers is, and you would work it exactly the same, you know, divide about, you know, one layer, if it divides it in half, then that's your half-life. If it takes 2, then your half-life is 2. If it takes 3, your half-life is 3.
So will it say like, what would be the three half value layers of it? Is that how they would kind of word that? I know that sounds weird. but
3,
I don't
I'm
know,
not
like,
sure I'm following.
how would they word a question like that? Or how would you word a question?
Wow.
Yes.
It depends on what day I wake up, you know? No, I don't know, I guess it could be, you know, a couple of different ways, you know, it could be asked, you know, if a half value layer of an X-ray tube is 1 millimeters of aluminum, how much aluminum would it take to cut the intensity of the exposure down to 1/4?
Oh, okay.
So that would be 2,
Yeah.
because it'd be, 1 would be
50.
1/2, and 2 would be 1/4.
Yeah.
So,
So expect corrections.
I feel that you are a little worried about math.
Joe's a great tutor, but I've only met him once. I'm not
Yeah, you know, are you more comfortable with decimals? No.
I probably shouldn't say.
Probably shouldn't say. Yeah, well, yeah, I mean, and there's not gonna be a tremendous number of you know, half value layer and half life questions on the test, just, you know, probably 2 or 3 tops. So, you know, that shouldn't sink you, but yeah, you know, half is half, quarter, 1/4 is, you know, half of a half, 1/8 is half of a quarter. So, I don't really know how to, you know, how to ease your mind on fractions or decimals. Okay, well, look it over, and I'll give you, you know, just a few minutes to look it over, and if there's something that, yeah.
The calculating the number for the shells thing,
Yeah, 2n squared.
I don't remember what the end number would be though.
The n is just the number of shell counting from the inside out. So the n shell, or the k shell rather, is your first shell. So,
And so that has 2,
yeah,
so it's
Yeah.
like K, L, and it would be like this, Nicole, K, L, and it.
yeah. So remember, there's a couple of things on the number of electrons you can have in a shell. Number one is that theoretically, any shell can hold a number of electrons defined by 2n squared, right? So, again, you've got the nucleus, and then your K shell is your first shell. K equals 1, L equals 2, M equals 3, and so forth. So that number right there is your N.
Oh,
Okay, so 2n squared means that number, or that number, right? So it'd be 2 times whatever number that is, so if we're talking about the M shell, so it'd be 2 times 3 squared equals what? What's your order of operation? You gotta get rid of that thing first, so 3 times 3 is 9, so 2 times 9 equals 18. Right, so that's number one, is that the maximum any shell can hold is 2n squared. The maximum number, the outer shell, regardless of what the outer shell is how many? 8, right? Okay, A couple of things also about the shells, the binding energies of those are going to be, really proportional to two things. One is the size of the nucleus. Remember, we used the Earth, the solar system as an example, right? And the planets closest to the sun had a more circular orbit, right? Because they had a very strong gravitational pull. So we kind of use gravitational pull as a example or an analogy. So the closer that you get to the nucleus, the greater that gravitational pull, and the stronger the binding energy. The binding energy equals gravitational pull, right? So the greater these two are attracted to each other, and therefore the harder it is to move them out, to get rid of them, right? So binding energy is highest close to the nucleus. And also, the larger the nucleus is, and we used the example of different planets in the solar system. We said that Jupiter had a much higher gravitational pull than what the Earth does, right? It kind of works like a vacuum cleaner, really, in the solar system. It's so big with a larger gravitational pull. If we didn't have Jupiter, we'd probably get hit by a whole lot more space debris than what we do. So Jupiter has a larger gravitational pull. It's like 2.3 times or something like that what the Earth's gravitational pull is. So the larger the planet, the stronger the gravitational pull, and the stronger the gravitational pull, the more tightly bound those electrons would be. So we got two things on binding energy. It's higher closer to the nucleus, and it's higher with big nuclei. What determines the size of the nucleus?
Amount of nucleons in it?
The number of nucleons, but especially, we're talking about atomic number here. What determines atomic number? Protons. Protons are which charge? Positive charge. Again, that's something that people trip over sometimes. They in this test, they somehow or another get, well, that may be why right there, protons and neutrons in the nucleus, right? So protons equal positive charges equal atomic number. So bigger the atomic number, bigger the nucleus, bigger the nucleus, the greater the binding energy.
Whenever it's regarding the isobar, the isotone, and isomers, whenever you ask for difference in electrons, different in protons, and different in neutrons, is that like just, am I thinking too hard on it? Is it just as simple as?
Yeah, no, really, isotopes are probably what's going to be represented on the test more than anything else. Isotons, isomers, isobars. I'm not going to have you calculate the number so that you come out with the right nuclear mass, So the difference in isotopes, for example, what's different between two atoms with different isotopes? And really, fundamentally, that's of those four, probably the most important thing that we understand. Number of neutrons, yeah. So it's just number of neutrons. Neutrons are which charge? Neutral charge, right. But yeah, you're not going to have to calculate all of that.
And then the mass is just protons and neutrons. Electrons don't count because they're just zero.
Right.
Okay.
Yeah, the mass number, no, it's just protons plus neutrons. Yeah. The things, yeah, never mind. That was the last test. I'm trying to confuse this test and last test. Let's not do that. realized, you know, I got back to my office one day and, you know, sometimes I'm recording a video and, you know, need to edit something out. I can actually edit the video, so I was actually watching through one of the sophomore videos. I realized how much I fidget with these pens. Is there, take the cap off, put the cap on, take the cap off.
Whenever it says like what is electromagnetic radiation, in the book, it doesn't really go into much detail other than it's being X-ray and gamma rays. Is that kind of what, as much detail as we'll need to know for?
No, there's a lot of different levels of electromagnetic radiation. Electromagnetic radiation is any kind of energy that exhibits both electric and magnetic properties. Okay, so in this chapter, you know, it did mention X-rays and gamma rays. X-rays and gamma rays are a type of electromagnetic radiation, but if you flip over to page 49, you see all the different types of electromagnetic radiation. So 3 things about electromagnetic radiation. One is it demonstrates electric and magnetic properties. That's number 1. And number 2 is that, that's 1 and 2. Number 3 is that it all travels at the same velocity, and that being the speed of light, right? So, in this chapter, in chapter 2, it does mention electromagnetic radiation kind of as a subset of ionizing radiation. It's important to understand that not all electromagnetic radiation is ionizing radiation, right? Visible light does not ionize. Heat necessarily doesn't ionize, right? So not all forms of electromagnetic radiation or ionizing radiation is upper end. So you've got X-rays, gamma rays, and you've got, what do you get? The sunscreen? Ultraviolet, thank you. So I would argue that ultraviolet is probably some degree of ionizing radiation. What we're going to learn in chapter 3 is that electromagnetic radiation exists on a continuum. And a continuum just means that it never ends, right? So low energy to high energy, there's overlap in between. So low energy ionizing radiation and high energy non-ionizing radiation probably overlap. So higher registry ultraviolet light probably does ionize. And, you know, again, whenever you get a sunburn versus radiation burn, in the early stages between the two, they're identical. You can't tell the difference between them. Later on, you know, when you start to blister from a sunburn, you'll actually get pretty much breakdown of the skin in radiation burns. So it's deeper and much more significant. I would say that ultraviolet probably is on some level ionizing. Now, the other thing in that is that it kind of puts electromagnetic energy in with alpha particles and beta particles, right, which are both ionizing radiation. So X-rays and gamma rays are not the only type of ionizing radiation. You've still got particulate radiation, which is ionizing as well. So not all forms of electromagnetic radiation are ionizing, and not all ionizing radiation are necessarily just X-rays and gamma rays. Does that make sense?
When it asks what does the atomic mass number indicate and the relative size of the sum of atomic particles, again, that's just
Yeah, that just means that the proton and neutron are massive, and the electron just almost doesn't exist in comparison. And the neutron's slightly larger than the proton.
Because it has both.
What's that?
Because it has both.
Yeah, because it has both. You know, that's my opinion anyway, is that it's got both and something sticking them together, and that makes up the additional mass. No.
We had some confusion on the force of the binding energy. In what types of atoms is it greatest, and then in what types of atoms is it weakest?
The types of atom that it would be greatest would be the higher atomic number. So the higher the atomic number, the stronger the binding energy, and then the smaller, you know, the lower the atomic number, the weaker the attraction would be.
So the greatest would be larger?
Larger,
Okay.
yeah. Larger nucleus, a higher atomic number, and also the position in the shells, the closer it is to the nucleus, would also increase the binding energy. So you know, that wasn't asking specifically what, you know, carbon versus lead versus uranium or anything like that. It's just size of the nucleus, bigger nucleus, as determined primarily by atomic number.
Oh, there was the formula for electron binding energy. Do we have to know that?
A formula for electron binding
Like
energy?
explained it and it said like how to figure it out
Oh,
and
Lord,
stuff.
no. No.
Okay, because I saw it, I was like, oh my god.
No. It looks
Okay.
kind of like kinetic energy. It's got
Yeah, but it was
squares
like
and halves and.
scarier than
Yeah.
that.
Yeah.
Okay,
No,
just checking,
no,
because
no.
I wrote it down.
I don't wanna work that, and I gotta work it to figure out, you know, no, I'm not gonna work that.
Thank God, thank you.
Anything else?
Maybe just real quick, the centripetal force, centrifugal. I can't-
Centrifugal force? Yeah, okay. Okay, so you've gotta have two forces, working together. One of these days I'm gonna bring a bucket with water for one of these classes, actually do it. So you're gonna have two forces working together. One is gravitational pull. That's your centripetal force. And if the two don't basically equal each other, then you're gonna have a problem, okay? So one is the speed of the electron as it travels around the nucleus, and the other is the gravitational pull, right? So you gotta have both of them working together, and if you don't, if the speed gets too low, and again, we use, the planets as an example here, Mercury, if Mercury wasn't traveling as fast as it's going, then what you would have is Mercury, the gravitational pull of the sun would pull Mercury into it eventually, right? It just suck it right up. So you gotta have two things going on. You have to have the centripetal force holding it into its orbit, but you also have to have the centrifugal force also kind of holding it into its orbit, in that it's going fast enough to not fall into the sun, but not so fast that it spins out into the rest of the solar system. Okay, so you gotta have both of them going on. So centripetal force holding it into its orbit, and it would fall into the sun if you didn't have the centrifugal force keeping it out, traveling, making it travel fast enough to keep it from falling into the sun. Is that, yeah. I always want to invert those two. I don't know why. Been doing this for a long time. I still want to invert those. Anything else? All right, and everybody's going to be here on Friday, and we're just going to split up between this classroom and 216, 217. I don't remember which one on Friday. It seems like it's 217. And that way, Trina's going to continue to test on Wednesdays and Fridays. I just don't think we're going to have enough time in the semester to cover all the material and review the test and test on two separate days. So we're just going to have all hands on deck on test days and just get it all over with in a single day, just to make sure that we have time enough to finish the material for the semester.
At 9:30, right?
Yes.
Okay.
Yeah. Yep. All right. And have fun in lab.